Good evening once again. We started our discussion on Thursday on introduction to inferential statistics. We talk about inference, sampling distribution, standard error. I talk about central limit theorem and hypothesis testing. So today we want to discuss confidence interval. Remember I said there are two inferential methods we want to discuss. We have discussed hypothesis testing. It's one inferential method. So we want to look at another inferential method, which is confidence interval. And after that, we'll be able to compare the two, the usefulness of both, and why we use them together. The other two methods of inferential methods are not commonly being used commonly, and but Bayesian or Bayesian theorem or method is increasingly popular now, while the other one, Monte Carlo's method, is not actually popular. But however, let's dwell on these two, the hypothesis testing and confidence interval. For us to start discussing confidence interval, it's good to understand some things like a point estimate and interval estimate, confidence level. Then we now continue our discussion. What do you understand by estimate, point estimate, and interval estimate? If you remember the other time, I said that a researcher is interested in what is in the population. And that phenomenon that is interested in the population, the way they summarize this phenomenon is by calculating parameter. You use parameter to summarize the phenomenon in the population. But because most of the time the population is very large, that you cannot attend to all the elements in the population to collect data from them. You now take a sample, which is a subset of population. And whatever you summarize the characteristic you will have summarized in the population, when you summarize in the sample, what you have is not parameter, it's statistics. So the statistic, statistic without S, it only takes X when it is plural. So that statistic is an estimate of the population parameter. The statistic belongs to the sample. It is summary of the characteristic in the sample. But the summary of the characteristic in the population, which you're actually interested in, is called parameter. So statistic you calculate from the sample is an estimate. It's just an estimate of the parameter. In as much as you don't use all the elements, you didn't collect your data from all the elements in the population, the parameter and statistic can never be the same. Cannot. The parameter may be closer to statistics. The statistic may be closer to parameter if you increase the sample size. Of course, we already said that when you increase sample size, you reduce the standard error. So when you reduce the standard, we already said that if the standard error is small, it means that the estimate, the statistic you calculated, the estimate is very close to the parameter. So the value of the statistic is an estimate of the parameter. So most of the time, when you calculate that estimate, is a value. We call it point estimate. So intelligent people now thought of it. Since we are not sure if the statistic we are calculated, which is the estimate of the parameter, we are not sure how close is it to the parameter. So because of that, the intelligent people thought over the years that, okay, what do we do? The first thing that came to the mind of those people, the pioneer of all these statistical techniques, was, okay, that value we calculated as the statistic is one value. It is called point estimate. Now, it's better to have since you are not sure, but it's better to have an interval that, okay, it will be safe. Instead of you saying, okay, this is the value, we believe that is equal to the parameter. You may say, okay, let's give a range of value within which you can say, oh, the parameter is. For example, now, if I want to guess somebody's age now, if the person is 38, and I just say, oh, you are 34, you have missed, or you are 36, I have missed it. But if you say you are between 36 and 42, you know, that 38 is already embedded in it. But if I say you should be between 35 and 45, in that one, I give a range of value. The probability of the actual age being captured in that range of value is higher when the range is wider than when it is narrow. Because somebody just, oh, you are between 39 and 41. You know, if the person is 38, you have missed it. Though you have given a range of value, but because it's a narrow range of value, but if you give a wider range of value, you are likely to capture it. So that is what the confidence interval does. So the interval estimate now is a range of value within which we can be maybe to a certain degree sure that the population value, the parameter will be any value in between these two range of value. And not only that, since different range of value will give different level of assurance. So for each of the range of value you give, you can attach to it the degree of assurance or confidence you have that this range of value will capture the real population value, which is the parameter. And that confidence is also called confidence level. For example, now, when I give an example of narrow range, wider range, your level of confidence is higher with the wider range that, yes, this range of value I'm giving, the population value will be anything in between. So confidence interval now is a range of value within which you are to a certain degree confident certain degree confident that the true population value will be in between these values as confidence interval. So you can have the confidence interval of the mean, because we know that when we summarize our sample, we get statistics. Statistics depends on the type of variable. If it is categorical variable, you'll be talking of proportion and rate. If it is a numerical variable, you'll be talking of mean to summarize it. So now you can calculate the mean and calculate the confidence interval of the mean. You can calculate the proportion, which is a percentage, and calculate the confidence interval of the proportion. You can calculate the rate and calculate the confidence interval of the rate. And you can calculate the difference, you know, when you are dealing with two. Instead of one sample, one group, you're having two groups. You would like to look at, say, okay, prevalence of anemia between urban and rural communities. There are two different populations, urban and rural communities. So you are going to get, by the time you say, oh, this is the level of anemia in this rural community, this is the level of anemia in the urban community. You know, it will give you different value. You can find the difference. What is the difference in this level? The difference may be 5, maybe 2%, maybe whatever. That confidence interval, the difference, you can calculate it also. So the difference between me, the difference between proportion, you can calculate confidence interval. Now, this one is just trying to show you what I said before. When you have, okay, for example, if it's, look at this table, it shows the type of parameter you want to estimate. On the vertical axis, you can see continuous variable or dichotomous variable. This dichotomous variable is like saying categorical variable. No, I told you that time. Even naturally, not all the categorical variables are dichotomous naturally, but they are still dichotomous in the sense that you can collapse the group. I told you. For example, now when you see ethnicity, Hausa, Igbo, Yoruba, Hausa, Igbo, Yoruba, others, you can, if you know, you have many categories now. When it is only two categories, like maybe we say religion, Islam, Christianity, male or female, that's dichotomous variable. That is, it follows binary or the binomial distribution because there are only two possible values. But when you have more than two values, like this case of Hausa, Igbo, Yoruba, others, you can hold one and say, compare with the rest. See, Hausa, what proportion Hausa, what proportion other? Igbo and others, or Yoruba and others can be, you know. So anything categorical by nature can be dichotomous in the sense that you can choose one, you can divide, you can collapse the groups and collapse into two categories. Or you choose one group, collapse the rest to compare that one group, one category with the rest. So that is why, by nature, any categorical variable follow binomial distribution. Now, continuous variable means you can know there are infinite number of values between two given value. So if it is one sample you are dealing with, look at the horizontal number of group, one sample, like descriptive studies, only one group. In that, you can calculate what you're estimating there is mean for continuous variable, while for dichotomous proportion, rate, prevalence, cumulative frequency, incident rate, those are the things you get. If you are dealing with two groups, two independent samples, you are looking at difference between mean for the continuous variable, for this order, different in proportion, different in rate, different different risk ratio, different way. You can calculate odd ratio, attributable proportion. Now, if you are dealing with two samples that are related, we call them dependent sample. For example, when we say dependent sample now, you have, for example, now when you say you measure some people's blood pressure while they are sitting, they stand, you measure. You have two readings, but it's the same group of people. There are 20 people. You record 20 values sitting. Or the same group of people, the same persons to stand up, you record their blood pressure. So the reading, there are two readings, but they are related. They are not independent. Because if somebody measure higher than another person, standing, the probability that he measure higher than the other person is very high also, because the two readings are from the same person, so they are dependent. That's why they call dependent sample or paired. Paired mean that. So pair, the word pair, when you say pair group, pair sample, it means independent sample. That is, actually, the word pair is in the misnomer. It's supposed to be, when you hear pair, you hear pair. You think maybe you have two people, you are pairing them. No. It's not the people, the subject that are being paired. But what is being paired is the observation, the data you collected. So for one person that may be Joseph, you have taken the blood pressure sitting and standing. So you record this for Joseph sitting and standing. So you pair sitting and standing blood pressure on Joseph. It's the observation you pair. It's not the individual. Because you'll be thinking when you say pair group, it should be two independent groups. No. Pair is not the group that is actually pair, it's the observation, the data you collected. The data you collected that is actually pair. So two dependent sample or pair sample. What you are looking at is different between mean and different between proportion. Now, this one is repeating what I just estimate. It's just using the notation we use to represent statistics and parameter. I said that the difference or the difference between statistics and parameter is so fundamental that even there's a system that now represent the statistic by Roman figure, Roman letter, not figure, Roman letter, and now represent the parameter by Greek letters. You see, by X for mean. So mean of mu. Mu by S of mu. By S that is the mean for the sample. Mu is the mean for the population, which is the real parameter. L square here is standard is variance when you square standard deviation. Variance for the sample, then rho square is the variance for the population, which is the parameter. Can you see that? It just so what it's telling you is that the estimate by x is the estimate of mu. L square is the estimate of rho square. Because this mu and rho square, they are parameters in the population. While the S by x and S square is rather statistic for the sample.
So can I
You want to ask question, you can ask a question.
yes, that's independent and dependent mean the slide before this one. Please, can you when you say two independent samples and two dependent samples, I'm trying to understand. Is it like when you take before and after?
Yes, that's okay. Maybe I didn't use the word. That's what they call, yes, another name is before and after. If you
That's
see
it.
that, yes,
Which
that's dependent. Dependent is the before and after. Independent are two separate.
two
If I
different
say
people?
I take blood pressure of male and female now, male one group, female another group. They are two independent groups.
Okay.
It's different from when I didn't differentiate between male and female. And I just say, sit down, I took your blood pressure. All of you stand up, I take the blood pressure. You know, you can, the two reading for each person, can tag the two readings for, so it's the reading that dependent group. So when before and after is dependent group. Why? Where you take measurement from two group of people, they are independent group. Is it clear now?
Yes, thank you.
So just to explain the same thing I've said, point estimate and interval estimate. An estimate of population parameter may be explained in two ways. I've already said it. One point, just one value, or you give an interval. So how to calculate that interval? That's where we're going now. Now, the point estimate is the one in the middle. So you now have the interval. You have lower limit, confidence limit, and upper confidence limit. So of course, the lower confidence limit will be less than point estimate. And upper confidence limit will be more than, greater than the point estimate. So the interval between the two limits, lower and upper, is the width of the confidence interval. And so we have already said it's a range of value. The confidence interval is a range of value. So a range of values are likely to include population value with certain degree of confidence. So the confidence is expressed in percentage, whereby a population parameter lies between an upper and lower interval. Look at this diagram now. You have the mean to be 4.28. The lower level is 2.92. The upper is 5.62. So now, between the if you the thing has been plotted using a normal distribution, we have already said that the area under the graph is 100% or 1. So here now, we have 95% in the middle. So the 95% is between the lower and upper, while the remaining 5% is outside. So less than the range, less than the lower limit, we have the 2.5%. Higher than the upper limit, we have the 2.5%. It's a clue to how we calculate our confidence interval. So this example we give is an example of 95% confidence interval, in the sense that the level of confidence here, the level of assurance you have here is 95%. You are 95% sure that this value we have calculated with the sample, for the sample, in the population, it will be between these two value, lower and upper limit, and you are 95% confident, sure. Now, how do you do it? The point estimate, you calculate the point estimate first. It's actually a point estimate plus or minus Z times standard error. We have already talked about standard error before in the last lecture, where we say standard error is standard deviation divided by square root of sample size. So if you calculate the standard deviation, you just divide by square root of sample size. It gives you standard error. But the Z is a constant. You remember, this is the standard deviation, number of standard deviation away from the mean. No number of standard. We remember when we were saying, when you plot normal distribution, many things follow normal distribution. But when you plot many things, it gives you different shape, even though it will still be bell shape, bilaterally symmetrical. But every other thing, the bulginess, the spread differ. So that's intelligent people now overcome this by developing only one standard normal distribution. And the way they did it is to, for any variable you are measuring, you calculate the mean. You now remove, you now know, okay, for each value, how far away from the mean for each value. You remove the mean from each value to really know how many standard deviation away from the mean each value is. That number of standard deviation away from the mean is called Z-score. I've explained it when we're talking about probability and normal distribution. So it's the same Z you see here. We know that we have already said that in between -1 and +1 standard deviation, we have 86, 68.4 to just 27%. While in between -2 to +2 is 95.45. But the researchers, they are interested in the middle 95. So the middle 95 is confidence level, which is what we are calling confidence level now. The middle 95 is in between -1.96 to +1.96 standard deviation. So that value, which is, so if we are trying to calculate 95% confidence level, we now, that value will be 1.96. That's Z, 1.96. Can you see now? You now multiply that 1.96 by the standard error. So whatever you get, you now remove it from the middle value, which is the point estimate. It gives you the lower limit. You now add it to the point estimate, it gives you the upper limit. That's why they say plus or minus point estimate plus or minus Z standard error. Where Z is the value for the standard normal distribution for the selected confidence level. So if you choose 95, you get 1.96. If you choose 99, you get 2.8. Now, also known as they say reliability factor. They say that Z is called reliability factor. In practice, we often do not know the value of the population standard deviation rho. However, if the sample size is large, greater than or equal to 30, then the sample standard deviation can be used to estimate the population standard deviation. So you are familiar with this. I show us this graph when we're talking about normal distribution and probability and normal distribution. That's what I used to explain, that standard normal distribution. So can you see the middle 95? Can you see minus 1.96 to plus 1.96 standard deviation? Confidence interval estimate, you see that is point estimate minus reliability factor, which is the Z, times standard error. That's the lower limit. Then point estimate plus reliability factor times standard error, that's upper limit. So the way by X minus reliability factor times, this is the formula for standard error. Standard deviation over square root of sample size. That's the lower limit. Upper limit is by x plus Lagrange factor times standard error. Give you the upper limit. So the higher level of confidence interval, this corresponding z-score, 1.645, that's for 90% confidence level. Nobody use 90% because it's too small. People use 95, then 99%. For 95, it's 1.96. For 99, it's 2.5. Sorry, I did say 2.8. It's 2.58. 2.58 or 2.576. So, confidence interval. What is just to revisit 95% confidence interval. What it means is that if you were to take 100 different samples and compute a 95% confidence interval for each sample, then approximately 95 of the 100 confidence interval will contain true value. Do you get it? If you take 100 sample, and you compute the 95% confidence level for this, 95 out of the 100 we include the real value in the population. That's the meaning of 95% confidence interval. Now, I think confidence interval for proportion, you can have it for proportion from mean. You know, the proportion, that one follows Z distribution, mean, T distribution, also, all those are just the like jargons, some of the things we have discussed. I think we have talked about degree of freedom before. So if you want to develop, when we get to T distribution, we'll talk much about this. When do you use Z? When do you use T? We'll explain better when we get to for this introduction to inferential statistics. When we get to T test, we tell them the reason people don't use Z test. They only use it for proportion. They only use for proportion. They don't use to compare mean because of some reasons, which we will discuss later. That's on the subject now. The confidence interval of proportion. The formula is a little bit tricky. Look at it. It's just for you to know the logic, because all you need to know is how to use your computer to analyze. So all these too much cramming of this formula, I just put these are the relative risk or ratio. Don't give it. Now, I want us to look at it. This graph is showing diastolic blood pressure. The horizontal line is the mean diastolic blood pressure in the population. That horizontal line. And some people took C samples and now measured the systolic blood pressure, and now calculated the mean and the 95% confidence interval for each of those C samples. How many of these C samples contain the population mean? How many of these C confidence interval contain the real parameter, population value? You can unmute. It's a lecturer. It's supposed to be a class. If it's physical class, I can ask questions. You can unmute and answer. Out of these 6 samples, how many of the 6 confidence interval contain the real population value? No answer. No answer.
At least 4.
Yeah, it's 4. It's not at least 4. It's 4 of them. It's 4. The number 2, number 3, number 5, and number 6. So that number 1 and number 4. If you see number 1, everything is below the mean, both the lower and upper limit of the confidence interval. And for sample 4, number 4, I'm just counting from the left to right. For number 4, that one, everything is above the mean. So it's only number 2, 3, 5, 6 that cross the mean Because I already told you the population mean is that horizontal line. So it's only 4 out of these 6 samples that contain the real population value. That's how to conceptualize confidence interval. Now, let's look at
I don't
compare.
understand.
Okay,
I don't understand how we arrived at 4.
how many
Ah,
samples there?
why is it the 4? As in, why is it number 2, 3, 1, 2, 3, 4, and 5? I mean,
2, 3, 5, and 6.
2, 3, 5, and
That's
6.
the one that contain. You can
So the
see.
one that cross the mean.
Yes, that's
Okay.
the one that the mean cross. Yes. So the population value is that level. You know the value is vertical. You know
Mm,
the value is vertical. The sample is horizontal. So for that number 1 and number 4 now, you see that both the upper limit, lower limit, and upper limit, they are not even up to the mean population mean. So the population, it does not capture the population mean. For the
okay.
number 4, both the lower and upper, they are above the mean. The issue is that it does not cover the population mean. But all these number 2, 3, 5, 6, somehow, they capture the population mean at one point or the other
The
along the
other.
interval. Does it make
Okay.
sense now? So that
Yes.
was all I was saying the other time. The meaning of 95% confidence interval is if you take this sample 100 times, out of this 100 times, you calculate the 95% confidence interval also. 95 will cross. 5 will be the way this number 1 and 4 is. 5 will be answer will not include the population value. 95 out of 100 will include the population value. Does it make
Okay.
sense?
Yes, sir.
Thank you. So now, many times when we discuss hypothesis testing and explain the meaning of p-value and how to interpret it, many people say, because it has been tricky for them to understand. Thank God they understand. But when we now say confidence interval is preferred over p-value. So, like if you want to publish in some high impact journal like Lancet, they don't take p-value from you. They don't take p-value. Because in fact, they speak against it. They say that p-value has no place in medicine. Has no place in medicine. They say it started with agricultural research in early 90s when they just dichotomize study into significant and not significant. So you see the reason they say that. Because the p-value just tell you that this is significant, this is not significant. Because it's probability that the observed value is due to chance. If the probability that is due to chance is so slim, that's we cannot say it's due to chance. Let's say it's a real difference. Which I usually call probability that of committing type 1 error. It's the same thing. Depends on the way you perceive it. So can you see? You just look at the p-value, significant, not significant. Once is less than or equal to 0.05, say significant. Once is greater than that, say not significant. That's all. So it just tell you if it's significant or not. But what they are advocating for is that the confidence interval give much more information. Yes, you can also know, you can equally know that this thing is significant or not with confidence interval, just like the way you know with p-value. He does the same thing the p-value does, but he now does something, 2 things extra that the p-value cannot do. So apart from knowing that it's significant or not, he give you the estimate. He give you an estimate. He give you a value. If it's different, you are looking at, he give you the difference. For example, now when we say the difference between proportion, he give you the difference. Or if we may calculate odds ratio, we call it, we'll still do it. We call it measures of association. Relatively, you quantify. These are measures of, you quantify association. Unlike people that just say there's an association, there's a significant association, that's all. The significant association, you cannot quantify how big is the significant association, you don't know. People cannot tell you. But confidence interval will tell you. Like all those odds ratio, the difference between me, relative risk, other, they are quantification. Can you see now? So p-value with a confidence interval will tell you if it's significant or not. It will quantify the difference. Then it will now give you a range of value within which you can find the population value. And even with that range of value, though is the range of value from the range of value that's where you can even know if it's significant or not. Can you see? There are three information. So those are the three information provided. The first one, estimate of the difference. The confidence interval give you, p-value does not give you. Can you see that? That's why the under confidence interval, yes, p-value, no. P-value cannot give you the estimate of the difference. The confidence that give you the estimate of the difference. Whether or not the difference is statistically significant, yeah, the confidence interval give you, the p-value give you also. But the third one, the range of value within which one can find the population parameter. The confidence interval give you, the p-value does not give you. Can you see that? Out of the four important information, the p-value give you only one. Out of three important information, the p-value give you only one. Why the confidence interval give you everything. And that is why, yes.
You okay, when you finish, sir. When you finish.
Yeah, so when you look at it like if you want to when you want to do your decision, there is no information p-value give you that confidence now or not give you. But most of the time, because even the examiner, if you are going for exam, the examiner may not even know how to interpret the confidence interval. You say, when we do different between we do t-test, we put different between means and confidence interval and the t-value and the p-value. You are showing two inferential methods. You are showing both. You are using both hypothesis testing and confidence interval, both to show the same thing. But if you remove p-value, say, oh, because confidence interval give more information, you remove p-value. The people that cannot interpret it will be looking, where is your p-value? The same thing when you do logistic regression. You have the watch statistic and the p-value, because the watch statistic is a chi-square, form of chi-square. That will give you the p-value. Then you also have the odd ratio and the confidence interval of the odd ratio. So normally, odd ratio with the confidence interval is enough. You don't need to be bothering yourself with the p-value, because many people they may not know how to interpret the odd ratio and the confidence interval. So they will now say, where is your p-value? That's why we show the two inferential method at the same time. So the relationship between, yes.
Okay, my question on that slide is, I've always seen p-value and confidence interval as two sides of a coin. Like if I say my p-value is less than 0.05, I assume that the confidence interval is 95%. I just see it like, okay, if confidence interval is 95 is the balance that is the p-value. I don't know. I've always seen it as two sides of a coin, that they complete a different. I don't know if I'm right.
Yeah, the issue there is that there's no, what that statement you just said is not completely correct. The issue of your level of confidence and your what we call is not the p-value and confidence level that are the same, and that we set level of significance. At what p-value level will you reject no hypothesis? P-value is different from level of significance. You know, I told you that time, p-value is like scoring an exam. Always score 50. You see, it has passed because the benchmark is maybe 40%. If it's in medical school or postgraduate, that everything is pass is 50%. So you just say the person just passed because 50%. If the person score 30, fail. So the level of significance is more like the cutoff point. At what level of the p-value will you reject no hypothesis? Will you say, oh, it's significantly and statistically significant? So you have to set that at the beginning of your study. Even it will reflect your sample size calculation. And once I've already said it before, let me repeat it. The level of confidence and the p-value, not p-value, the level of confidence and level of significance, they are complementary. They add up to 100%. So if your level of confidence is 95, your level of significance will be 5%, which is 0.05. That's what you are trying to say. It's not p-value and confidence. So those one you set it. So that is you have set it as your level of confidence you used to measure this is 95%. That's what the level of significance is 5%. So part of what you are actually wanted to ask is what the next slide, the relationship between confidence interval and statistical significance. So you cannot say it's two sides of a coin. It's not actually two sides of a coin. Because we have already said that in the two sides of the coin, one is give more information than the others. So the issue is when you say something is two sides of a coin, one side will give one information, the other one will give you another information that are complementary. So it's the same coin, which you can, when you have the same coin, you can. So it's not like that. You can do without p-value and go with confidence interval, because what confidence interval will give you, what p-value will give you, confidence interval will give you, and I'll give you two things in addition. So why bother about p-value, the confidence interval? Does it make sense now?
Yes, sir.
So that is why many times when you are doing your analysis, when you do chi-square, it's like a screening process. You have not concluded, because even a lot of things you see is significant with chi-square, there will be a lot of confounder. When you now do logistic regression, you remove the confounder. So that's where you have your definitive, take your definitive decision. At that point, you can do without p-value to interpret your result, because there's nothing. But the issue is that the relationship between it is that if it's significant with p-value, it will be significant with confidence interval. That is the two things that both of them have. You can know if it's significant with p-value. You can know if it's significant with confidence interval. And if it's significant with confidence interval, it will be significant with p-value. So it's not that, it's better you use confidence interval because it will be easily significant with it. When it is significant with confidence interval, it may not be significant. No, it's the same. It showed the same, but the only thing is that the confidence interval gives more information than the p-value. So that is why it's preferred. So this one, where should I even put it there? This one, T, 2T. Yeah, this one is just to add something. It's not part of this confidence interval per se, but it's part of, let's say, Inferential statistics as a whole. When you are doing tests, this one, and when you are doing maybe hypothesis test, you are doing tests, you are comparing two groups. You have to determine, are you using 1T or 2T? There are the difference between them, when you say something is 2T, you are having two groups, you want to know if there's a difference. What you want to estimate may be higher in group A, it may be higher in group B, it doesn't matter. For example, now, prevalence of anemia, urban, rural community. You may not vary your mind and say, yeah, anemia is usually higher in urban, in rural rather. It may be a lot of things that worse in urban slums. So you may do it may even be higher in urban than rural. Because you in rural may be eating natural food, everything, and they are okay. Whereas somebody in an urban slum may be anemic. So when you are doing your study, you have not predetermined that, this attribute you are measuring is higher in one group than the other. So in that situation, you just want to know, is there any difference between these things? Is there any difference in anemia between urban and rural? It may be higher in urban, it may be higher in rural. It doesn't really matter. That is 2T, because it's no direction as per one should be higher than the other. That's 2T. But there are some situations that it's only meaningful to conceptualize in such a way that one is higher than the rest, not the other. There are some examples that are very rare. But sometimes before I've read about some examples that can be like that, but after I forget, I usually fabricate one to explain in my lecture. The one that's fabricated is that imagine you have some women that are still giving birth when their first daughter is giving birth. Yeah, it happened. Now, the issue now is maybe you now have an antenatal clinic where mother come and the first daughter come also. They are pregnant at the same time. In that antenatal clinic, there are some mothers, there are some first daughters, some daughters that are with their mother, they are pregnant at the same time. You may now say, okay, let's look at the age. The age differ? Do the age significantly differ? And the age of these women significantly differ from the age of their daughter. If you want to do that, you cannot say you are doing two things because you know for sure that the average age of the mother will be higher than that of their daughter. It's not possible for the average age of the daughters, since it's the same daughter, they have their mother there and the daughters are there. So the average age of the daughter cannot be higher than that of their mother. The only thing may be so close that you cannot find much difference. So in that situation now, it's one thing in the sense that you have already known that you want to know, does the average age of the mother is it significantly higher than that of their daughter? So in that situation now, you already know that one is higher, but you just want to know that if that difference is significant, that is one thing. So you see, in one thing, there is implication. It is easily significant with one thing. When you are doing a test with one thing, it's easily significant than when it is two things. Look at it, the first one. That first diagram up is one thing, it's two things rather. You see that it's the same 95% confidence level you are having. You will see the area under the graph is 100%, and the middle 95 here, that shows that to the left is 2.5%, to the right is 2.5%. But the one thing, the 35% is on one side. So the last two, the second and the third graph now, is showing the same thing. It's showing one, A is higher than B, two, B is higher than A. It's just the same thing. It's just showing a different direction. So in this situation now, one side of that graph, 95, the other one is 5%. It's unlike the two things where we have 2.5, 2.5 on the estimate, because it's only one side. So the 95 is one side, the 5% is on one side. So if you start moving from the middle, you are calculating that standard normal deviation, which is z-score. From the middle, you will see that for the two things, from the middle to that place is 1.96. But the other one will be shorter, sure, because to each side for that, from middle to zero, you know what we have at the estimate is only 2.5%. But for this one, I want it. If you are moving from the middle now to that place, because it's 5%, it will take more area. So you will have reached estimate. That is why the z-score is 1.67 rather than 1.79 of the two things. Does it make sense now? So it is easily significant with one thing than two thing test. Thank you. Any question?
Thank you very much, sir. Thank you very much. The last slide, please. This last slide. Okay. I'm assuming this is theoretical. In practical terms, what does a one-tailed and two-tailed, like what kind of sample, what kind of test are we, what kind of study? Like, is it like a blood pressure? Can you give us a practical example of what kind
anything. Maybe I say I can. Is anything you are studying just like one, two things? Is any study you are doing bad? Here, you are looking at two groups. The attribute, it is known that it may only sense that is higher in one group than the rest. That the other, not the other. I keep on saying the rest. It's higher or is smaller in one group than the other. You already know the direction. When you are looking at difference between two groups, when you are looking at different groups in two things, anyone can be higher. I give an example now. If you say Unless if you already know that, for a case of anemia, now, if you already know that, oh, if you know anemia in this community, it's higher among the rural than urban. In that situation now, you may want to do tests to see is it actually significantly higher. And you see that you already know that anemia is higher in one group than the other. So you just want to now compare. We want to compare that rural and urban that it says lower in urban. So since you already know this higher, when you want to know is it actually significantly higher? Maybe the difference is not so much. It's one thing because you already know. You already made up your mind, known that it's higher in one group than the other, or it's lower in one group than the other. We just want to know that difference is it significant. That is one thing. But when you just want to know the difference between the two groups, but it can be higher anywhere. You don't have the premonition that it's lower or higher anywhere. That is two things. Does it make sense now?
Yes, sir. Good. Thank you.
Yeah, any other one? So no other question.
Hello, sir. Sir, there's a question.
Okay.
There was a place you told us about the sample size higher or lower than 30. Why the figure 30?
Well,
I don't know if I'm making
the figure 30 usually, if you go and check t-test and z statistical table, you know we talk about the degree of freedom. Are you following? Are you following? The person.
Go ahead.
So you know we talk about the degree of freedom. Like for example, now you calculate your degree of freedom. If you are doing t-test, if it's one sample t-test, the degree of freedom is the sample size minus 1. If it is two sample t-tests, the degree of freedom is n1 plus n2 sample 1 plus sample 2 minus 2. Or you say sample 1 minus 1 plus sample 2 minus 1 is the same thing. So you add the two samples together, you remove 2 because each of them you remove 1 from each of them. Now, the degree of freedom around that 29, you see that the 1.9, that because the 95% confidence interval we talk about that corresponding 1.96 is with normal distribution. But when you now get to T distribution, you know the T distribution, I said that we have not done till we explained that. That was why I just judged. I know that a lot of explanation is needed. That's why I just say, just leave that one. We'll talk about when you get to T test.
It's okay.
So at that particular point, you know, I already said that we talk about central limit theorem. Every other distribution, they tend to approach normality as their sample size increases. As the sample size increases, the degree of freedom increases. At that point, 29 degree of freedom, you see that that standard normal VDV 1.96 correspond with that of Z distribution. T will be 1.96 also. So at that point, that 30 is the value where T approximates Z distribution. That's why they use that word, you use that 30. So when we get to T test, we explain more about it.
It's okay.
Yeah. So somebody is making noise. Then somebody say, please, you did not send the link. Okay, last slide. Sorry. I just remember. I will send it together with this one. Sorry. I will send it together with this one. Any other one?